Welcome! In this lesson, we'll tackle LeetCode problem number 443, titled String Compression. It's a fascinating problem that tests your ability to manipulate strings efficiently. We'll explore the brute force approach and discuss its time and space complexities. Let's dive in. In this problem, we are tasked with compressing an array of characters using an in-place algorithm. The goal is to take the input array, which contains characters, and modify it to store the compressed version directly within the same array. The compression follows a simple rule. For each group of consecutive repeating characters, if the group has a length of 1, we simply keep the character as it is. If the group's length is greater than 1, we append the character followed by the length of the group. Once the entire array is compressed, we return the length of the modified array. Remember, this operation must be performed without allocating any extra space, so we're limited to 1 additional space beyond the input array itself. The input is a list of characters, and the output is the new length of the array after the compression is applied. Let's explore the mechanics of the problem with a concrete example. Suppose the input array is a B, B, C, C, C. First, we identify the groups of consecutive repeating characters. Here, we have AA, BB, and CCC. Compressing the group AA results in A2, meaning we write a followed by the number 2. Similarly, BB compresses to B2, and CCC compresses to C3. After writing these compressed values back into the array, it becomes a 2B, 2C3. The new length of the array is 6, which we return as the output. This example demonstrates how we systematically process each group and update the array in place. As another example, consider the input array, A. Here, there's only one group consisting of a single character, A. Since the group's length is 1, we leave it unchanged. The array remains, A, and the length of the compressed array is simply 1. Now, take a larger example of B, 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 B. The two groups are A and B, 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 B. The group A has a length of 1, so it remains as A. The group of 12 Bs compresses to B12. Writing this back into the array results in a B1, 2, with a compressed length of 4. Finally, let's summarize the constraints and edge cases. The input array will have a length between 1 and 2000, and every character in the array will be a lowercase English letter. Some edge cases to consider include arrays with a single character, such as A, which remain unchanged. Arrays with all unique characters, like A, B, C, won't have any compression since no group is longer than 1. On the other hand, arrays with all identical characters, such as A, will compress to A, 4. Additionally, very large groups, such as 15 consecutive A's, must be handled correctly by splitting the count into individual digits, resulting in something like A, 1, 5. These considerations ensure that the algorithm is robust enough to handle a variety of scenarios efficiently and correctly. To tackle the problem of string compression, we considered two primary approaches. The first is the brute force approach. Here, the idea is straightforward: iterate through the array of characters and manually construct the compressed string. For every group of consecutive repeating characters, we append the character itself, followed by its count, but only if that count is greater than 1. Once the compressed string is constructed, we overwrite the original array with this new string. However, this method is highly inefficient, especially for larger inputs. The reason lies in the repeated string concatenations, which are costly in terms of both time and memory. As a result, the brute force approach has a time complexity of O, n superscript 2, due to these concatenations, and a space complexity of O, n, because we create an additional string to store the result. On the other hand, the optimized in-place approach takes a more efficient route. Instead of constructing a separate string, it modifies the input array directly. This is achieved using two pointers, one for writing the result into the array and another for reading through the input. For each group of consecutive repeating characters, we write the character at the right pointer and, if the group has more than one character, convert the count to a string and write its digits into the array as well. Then, we move the read pointer to the next group. This strategy avoids the inefficiency of creating new strings and adheres to the problem's constraints. The optimized in-place approach offers significant performance advantages. Its time complexity is O(n), as we traverse the input array only once, and its space complexity is O(1), since no additional data structures are used. This makes it highly efficient for large inputs. We chose this approach because it strikes the perfect balance between simplicity and performance. By eliminating costly operations like string concatenations and additional memory allocation, it adheres to the constraints of the problem while scaling effectively. The two-pointer technique is central to this efficiency, ensuring that we handle the array with minimal overhead. While the brute force method is easier to implement, it falls short for larger inputs due to its quadratic time complexity and extra space usage. The in-place approach, though slightly more complex due to the need to manage pointers in edge cases, such as single character groups, is far more efficient and robust, making it the ideal choice. These trade-offs highlight the importance of optimizing for both time and space, especially when dealing with larger datasets. One key insight that made the optimized in-place approach so effective was the realization that we could directly write the count of repeating characters as a string into the input array. This eliminated the need for a separate string or data structure, streamlining the entire process. By leveraging this insight, we achieved in-place modification while maintaining linear time complexity. In summary, the optimized in-place approach is the best solution for this problem. Not only does it fulfill the problem's constraints by working directly with the input array, but it is also efficient and scalable. Using two pointers for reading and writing allowed us to achieve O(n) time complexity and O(1) space complexity, making the solution both elegant and practical. This method handles edge cases effectively, avoids unnecessary overhead, and demonstrates the power of careful algorithm design in solving complex problems efficiently. The problem we're solving involves compressing a given array of characters, chars, in place. The compression is done by replacing groups of consecutive repeating characters with the character itself, followed by the count of repetitions, but only if the count is greater than 1. The goal is to overwrite the input array with this compressed version and return the new length of the array. To solve this efficiently, we use two pointers. The write pointer determines where we write the compressed output, while the read pointer is used to traverse the array and identify groups of repeating characters. This approach is memory efficient because we directly modify the input array without using any additional space. We start by initializing these pointers and then traverse the array, grouping consecutive repeating characters. A count variable will help us keep track of how many times a character repeats as we move the read pointer forward until a new character is encountered. Once we've identified a group of consecutive repeating characters, we write the compressed output. The write pointer is used to place the character at its appropriate position in the char's array. After writing the character, we increment the write pointer. If the count of repetitions is greater than 1, we convert the count into its string representation and write each digit of the count to the array, again using the write pointer. For every digit written, the write pointer is increment. Once the traversal is complete, the write pointer will indicate the position just after the last compressed character. This value represents the new length of the compressed array, which we return as the result. The algorithm is built on three important insights. First, the two-pointer technique ensures the operation is done in place, eliminating the need for extra memory. This technique is key to minimizing space usage. Second, converting the count into individual digits allows us to directly write these digits into the array while preserving its in-place nature. Third, the algorithm is highly efficient, with a time complexity of O(n), because we only iterate through the array once, and a space complexity of O(1), as no additional data structures are used. The char's array serves as both the input and the output, while the read and write pointers manage traversal and writing. Lastly, the count variable helps track the size of repeating groups, ensuring the algorithm is both simple and efficient. When implementing this algorithm, it's important to handle several edge cases. For example, if the input array contains only one character, it should remain unchanged, and the length returned should simply be 1. If there are no repeated characters, the compressed array will be identical to the input. For large repetition counts, such as when a character appears more than 9 times, we must ensure that all digits of the count are written individually. For instance, a count of 12 would be written as 1 and 2. Additionally, if the input array is empty, the resulting length should be 0. To illustrate, consider the example input chars equals a, b, c, c, c. Initially, both write and read pointers are at position 0. For the first group, the character A repeats twice, so we write A at position 0 and 2 at position 1. The right pointer is then incremented to position 2. Next, for the second group, the character B repeats twice. We write B at the current right pointer position, increment it, and then write 2 at the next position before incrementing again. Finally, for the third group, the character C repeats 3 times. We write C at position 4, increment the right pointer, and write 3 at position 5. At this point, the array has been compressed to A, 2, B, 2, C, 3, and the right pointer is at position 6, which is the new length of the compressed array. This approach ensures the algorithm is both time and space efficient, with a time complexity of O(n), since each character is processed exactly once, and a space complexity of O(1), as the array is modified in place without any additional memory usage. To solve LeetCode problem number 443, string compression, we use a two-pointer approach to compress the given character array in place. The goal is to overwrite the input array with a compressed version and return the new length. We initialize 2 pointers, write to track where to write the compressed characters and read to scan the input array. The main loop iterates through the array using the read pointer. For each unique character, we count its consecutive occurrences using a nested loop. The char variable stores the current character, and we increment the count variable for each repetition. Once we move past all occurrences of the current character, we write the character to the right position. If the count is greater than 1, we convert it to a string and write each digit to the array sequentially. This ensures the array remains in place while being compressed. The function returns the right pointer's value, which represents the new length of the compressed array. This approach is efficient with O(n) time complexity, as we traverse the array once. It also uses O(1) additional space since the compression is performed in place. This implementation handles edge cases, such as arrays with all unique characters, no compression needed, or arrays with all identical characters, maximum compression. It ensures correctness and efficiency for any valid input. Here, we have the Java implementation of the string compression algorithm. First, we define a write pointer, which keeps track of where we write the compressed characters, and a read pointer, which iterates through the original array. The while loop ensures we process the entire char's array. Inside the loop, we begin by storing the current character in current char and initializing a count variable to 0. The nested while loop counts how many times the current character appears consecutively. This is done by checking if the character at the red pointer matches the current char, and if so, we increment both the red pointer and the count. After determining the frequency of the character, we write the character itself to the position indicated by the right pointer. Then, if the count is greater than 1, we convert the count to a string, break it into individual digits, and write each digit back into the array. This ensures that the compressed representation of the character is stored correctly. Finally, after processing all the characters in the array, the function returns the value of the right pointer. This value represents the length of the compressed string. By modifying the input array in place and returning the new length, the algorithm achieves both space efficiency and simplicity. This implementation is straightforward and handles the compression process in a single pass, making it optimal with a time complexity of O(n), where n is the length of the input array. To begin solving this problem, we start by initializing 2 pointers, write, which keeps track of where the next compressed character or digit will be written, and read, which scans through the input array. Initially, both pointers are set to 0. First, we process the character A. As we read through the array, we count consecutive occurrences of A. In this case, there are 2 occurrences, so we increment read to 2. We then write the character A to the position indicated by write, and since the count is greater than 1, we convert the count into its string representation and write it to the array as well. This updates write to point to the next available position. Next, we move on to the character B. Again, we count its occurrences, which is also 2, and repeat the same process, writing B, writing the count 2, and updating write. Finally, we handle the character C, which appears 3 times. We write C to the array, followed by the count 3, and finish with write updated to 6. At this point, the final state of the array for example 1 is A, 2, B, 2, C, 3, and the right pointer ends at position 6. This means the compressed length of the string is 6. Now, let's consider example 2, where the input array contains no repeated characters, A, B, C. Again, we initialize write and read to 0. We start with the character A, counting its occurrences. Since it appears only once, we write it to the array at the current write position and move both pointers forward. For the next character, B, we repeat the process, count its occurrences, write it to the array, and update write. The same steps are applied to the last character, C, where we write it to the array and finalize write at position 3. In this case, no digits are written because there are no groups of repeated characters. The final state of the array for example 2 is A, B, C, with write equal to 3, which represents the compressed length of the string. Now, for example 3, we have a mix of repeated and non-repeated characters. The input is A, B. We initialize write and read to 0 and process the character A. This time, there are 4 consecutive occurrences of A, so we increment read to 4 while counting them. We write it to the array at write, and since the count is greater than 1, we convert the count to 4 and write it as well. This updates write to 2. Next, we process the character B, which appears only once. We write B to the array and update write to 3. The final state of the array is A, 4, B, and the compressed length is 3. This concludes the walkthrough of the solution examples. The time complexity of the solution is O, n, where n is the length of the input array chars. Let's break this down step by step. First, we consider the outer while loop, which iterates until the red pointer reaches the end of the char's array. Each character is processed exactly once, as the red pointer advances through all characters in the array sequentially. This means the total number of iterations for the outer loop is proportional to the size of the input, or O, n. Next, we have the inner while loop, which counts consecutive occurrences of the same character. For instance, if a character is repeated k times, the inner loop will iterate k times. However, because the outer loop consumes all repetitions of a character in one go and processes each character exactly once, the combined iterations of all inner loops still remain proportional to n. Therefore, the time complexity of both loops together is O, n. Now let's analyze the time complexity of writing the compressed string back to the input array. Writing one character requires constant time, or O1, per character. When writing the count of repeated characters, the digits of the count are written individually as strings. Writing these digits takes O, log 10, count, time, as the number of digits in a number is proportional to its logarithmic value. However, the total sum of all counts across the array is at most n, meaning the total number of digits written is also proportional to n. For example, even if the counts are large, the total number of digits written is still bounded by the size of the array. Therefore, the time spent writing to the array also contributes O, n, overall. Combining this with the reading and counting operations, the total time complexity of the solution remains O, n. The space complexity of the solution is O1, as no extra space is used that scales with the size of the input. First, the input array chars is modified in place to store the compressed string, so we don't allocate any additional memory for the output. Next, the algorithm uses a constant number of variables, such as write, read, char, and count. These variables do not depend on the input size and contribute O1 space. Additionally, when converting the count to a string using str, count, a temporary string is created to store the digits of the count. The size of this temporary string is proportional to the number of digits in the count, or O, log 10, count. However, since this string is discarded immediately after use and does not scale with the size of the input array, it is effectively O1 in terms of space. Thus, the overall space complexity remains O1. To summarize the space complexity, the solution does not use any extra space that grows with the input size, so the total space complexity is O1. Let's compare this to a brute force or naive approach. In a naive solution, we might create a new array or string to store the compressed result. For instance, we could build the compressed output by appending characters and counts to a separate list or string. While this approach would still have a time complexity of O(n) for reading and processing the input, it would require additional space proportional to the size of the compressed string. This means the space complexity of the naive approach would be O(k), where k is the size of the compressed output. In contrast, the given solution achieves in-place compression and avoids this overhead, making it more space efficient with an O1 space complexity. Let's consider the time and space complexity in different scenarios. In the best case, all characters in the array are unique. Here, the count is always 1, so no digits need to be written to the array. This results in a time complexity of O(n) for reading and writing characters, and the space complexity remains O(1). In the worst case, all characters in the array are identical. The count in this scenario would equal n, and we would need to write log 10 n digits to the array. Even in this case, the time complexity remains O(n), as each character is processed exactly once, and the space complexity is still O(1). In the average case, which involves a mix of unique and repeated characters, the algorithm behaves similarly. Each character is processed exactly once, so the time complexity is O(n), and the space complexity remains O(1) regardless of the input. To formally prove the time complexity is O(n), consider that each character is read and written exactly once, and the total number of digits written for counts is proportional to the size of the array. This means the total number of operations is a constant multiple of n. As a result, the time complexity is O(n). For space complexity, the solution does not use any additional data structures or memory that scales with the input size. All extra memory used is constant, such as variables and temporary storage for digit conversion, which are effectively O(1). Therefore, the space complexity of the solution is O(1). One common pitfall in string compression problems is off-by-one errors in iteration. This often happens when the final group of characters isn't processed correctly, leading to missing the last compressed segment. To address this, ensure that after completing the main loop, you explicitly handle the last group if it hasn't been processed yet. Another mistake involves incorrectly handling single characters. For instance, appending a count even when it's 1 can result in outputs like A1B1 instead of the expected AB. To fix this, you should only append the count if it's greater than 1. Finally, modifying the input array incorrectly is another frequent issue. Overwriting elements without carefully maintaining the correct order or index can produce unexpected results. The best practice here is to use a separate pointer to track the position where you write the compressed string, ensuring the input array is updated in the right sequence. Another frequent mistake is overcomplicating the compression logic. When the conditions to handle various edge cases become overly complex, debugging becomes a challenge. A better approach is to break the problem into smaller steps, such as grouping characters, calculating their counts, and appending the results. Keeping the logic modular makes it easier to manage and debug. Additionally, some people ignore the space constraints of the problem. For in-place compression, creating a new array instead of modifying the input directly violates the requirements. To adhere to these constraints, you must modify the input array without relying on extra space. This ensures your solution meets the problem's expectations for efficiency. When preparing for interviews, it's crucial to fully understand the problem statement. Specifically for compression problems, clarify whether the compressed string must be shorter than the original. If this isn't stated explicitly, assume compression is always performed. It's also important to discuss edge cases during the interview. Examples include strings with no repeating characters like ABCDF, strings consisting of all identical characters such as AAAA, and very short strings like a single character or an empty string. A good strategy is to test your solution incrementally. Start with simple cases to verify correctness, then progress to edge cases. This demonstrates a systematic and thorough approach. Additionally, focus on correctness first by implementing a brute force solution, then optimize for time and space later. Interviewers value seeing a clear progression from basic correctness to efficiency. It's helpful to explore related problems to deepen your understanding of string manipulation and compression techniques. For instance, LeetCode 443, which is the current problem, ties closely to others like zigzag conversion, encode and decode strings, and group anagrams. Each of these problems provides opportunities to practice similar skills in different contexts. There are also alternative approaches to solving string compression problems. The two-pointer approach, for example, is highly efficient for in-place operations, but it requires careful index management to ensure correctness. This approach typically operates in O(n) time with O(1) space complexity. Alternatively, a hash map or frequency counter can be used for problems that require frequency analysis. While these methods are often easier to implement and debug, they trade off space efficiency by requiring extra memory. Choosing the right approach depends on the constraints and trade-offs of the specific problem you're solving. For certain problems, you might also consider a divide and conquer strategy. This is particularly useful when dealing with very large inputs where compression can be parallelized. The idea is to divide the array into smaller chunks, compress each chunk independently, and then merge the results. While this approach can handle large-scale problems effectively, it does introduce additional complexity in managing the merging process. The trade-off is worthwhile in scenarios where performance at scale is critical, but it's important to weigh this against the added implementation overhead. This method highlights how understanding the problem's constraints can lead to creative and scalable solutions. Great work! In summary, we tackled the string compression problem by exploring the brute force approach and analyzing its efficiency. Remember to practice string manipulation and in-place algorithms, as they're crucial for coding interviews. Don't forget to like and subscribe for more problem solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!